Okay. So everyone can see my slides, right?
Yes, sir.
Okay, so I'm hoping we'll be able to finish the Fourier analysis, the theory of Fourier analysis today, and we'll get back to the data in the next class. So this is where we were approximately speaking. We had talked about 4 types of Fourier analyses. The Fourier series, which is applied to continuous time signals that are periodic in nature, so continuous time and periodic in nature. And in the frequency domain, you get coefficients at at multiples of the fundamental frequency omega naught, which is 2 pi by t. So this is Fourier series. Then we talk about Fourier transform, which is for continuous but aperiodic signals. And then the Fourier transform is continuous in frequency. So this is discrete in frequency, this is continuous in frequency. And the formula, as you see, are quite complementary. So there's a duality there. You can see that it's just a sign change here, e to the power j omega t, and this is minus j omega t. So in the discrete time, we have got discrete Fourier series, just likewise discrete time and periodic in discrete and periodic in time. And in the frequency domain, again we get a discrete representation, but you only need n terms. You don't need an infinite number of terms like in the Fourier series. You need only n terms because after that they start repeating. And we have the discrete time Fourier transform, which is a discrete aperiodic in signal that is aperiodic in time. And then the frequency representation omega here is again continuous. This is the formula. So it is continuous in frequency, but it's also periodic in frequency because it repeats after every 2 pi. So in the discrete time, you only need to worry about what's happening between minus pi and pi, or equivalently 0 and 2 pi. After that, it starts repeating. Okay, so these are the sort of 4 classes that we had talked about in the previous few classes. And then now we are sort of putting this all together, and we are asking that if I take a signal and I try to discretize it, how does the frequency representation change? Okay, why is that question interesting? It's interesting because if you want to analyze and store and send or whatever, do something with the signal, I need to discretize it and store it in my computer. So I want to know what happens when I do that. Okay, so sampling a continuous signal, we did this in the previous class. You can think of a continuous signal being sampled by multiplying it with a train of impulse functions. So if I multiply pt with xt, I get the xpt. It is still a continuous signal. It just happens to be 0 everywhere except at multiples of 1 by t. And at that value, it's a delta function multiplied with whatever the value of the continuous signal is at that time, x0, xt, x2t, and so on. Okay, and what we saw, this is very, very important, is that in the frequency domain, if my signal is band limited, then is a point. This process of sampling essentially makes an infinite copies of the frequent, the signal in the frequency domain xj omega, separated by the sampling frequency. And this happens because the Fourier transform of this comb function is another comb function. The closer are these impulses in time, the farther they will be in frequency. So multiplying the signal with the comb function is equivalent to convolving the Fourier transform of the continuous signal, which is here, with the Fourier transform of the comb function, which is another comb function. Okay, so this is the convolution. This comes directly from the fact that time in multiplication in time is equivalent to convolution in frequency domain. And then I use the shifting theorem of a delta function, which means that whenever you convolve with a delta function that's sitting somewhere, you just basically take that signal and put it at that point. Delta function just shifts that. So essentially you end up getting one copy for each of the delta functions that are sitting in the frequency axis, and you get a representation like this. Okay, so this is the Fourier transform of my original xt, this signal, and this thing is the Fourier transform. This is still the Fourier transform because it's a continuous signal of this particular signal given by these impulses scaled by the time, by the value of the continuous signal at those times, x0, xt, and so on. Okay, and if you're sampling too fast, which means that these samples are quite closed in time, they'll be well separated in frequency, so that these the Fourier transform doesn't there's separation between these. But if you are not sampling fast enough, then there will be overlap. This is what is called aliasing. And you can always avoid an overlap if your sampling frequency omega s is at least twice that of omega m, the maximum frequency content of the signal. And this is what is called the sampling theorem. Let xt be a band limited signal with maximum frequency content of omega m, which means x j omega is 0 for omega mod of omega greater than omega m. Then xt is uniquely determined by its samples x and t if omega s is greater than 2 omega m, where omega s is the fundamental frequency, 2 pi by t. Okay. And how do we do this? How do I recover the signal from its samples? Well, the sample signal has a Fourier transform that looks like this. So all I need to do is multiply it with a ideal low pass filter, a rect function. When I multiply this, all these side lobes go away and I'm just left with the original thing. So I can take the Fourier transform, multiply it in the frequency domain with a rect function and take the inverse Fourier transform. Or equivalently, I can just convolve the signal with the Fourier transform of this, which is a sinc function, and I'll get back my original signal. Okay, so think about this, so if I've got, let's see if I can draw now. So if I've got a signal that looks like this, and I give you samples, just samples like these. So I give you those samples. So now you've got samples like those. If you convolve this sampled signal with a sinc function, you will get back this signal xt. Okay, and the sinc, why does this work? Because in the frequency domain, xpt has a representation like this, and the sinc function has a representation like this. In the frequency domain, it's a rect function. And then when I multiply the two, convolution in the time domain is a multiplication in frequency domain. I just get back the Fourier transform of xt. Okay. So any questions on this? This is what we have done in the last class. Okay, so let me ask you guys a question then. Let's see. Okay, so I can't change a pen color. Let's see. So tell me something. Suppose I give you just these signal samples. Okay. And suppose the actual signal did this or something of that sort. Now the sample is still the same here. Then how can I possibly recover the signal? How can I find out what the signal was doing between the two samples? It could have been the black trace or it could have been the red trace. They both have the same values at the sampled points, correct? So if I just give you the samples back, how do you know that it's not doing what the red curve is doing? It's only doing what the black line is. Because that's what I'm saying. You don't need to know what's between the two samples. So who can answer this? Anyone? You guys can hear me, right?
Yes, sir.
Mhm. So I've given you the samples. The samples are the same, the red and the black. So how do I know? I'm telling you that if I give you the samples, you can always reconstruct the signal back, which means it's okay to not know between the samples. But how can that be the case? Think and tell. Come on, guys, let's guess at least. What do you guys think?
Uh, Frequency of the each signal is different itself. So
Well, the signal has many frequency components, yes, but you're on the right track, yeah. So carry on.
so it is what I'm saying is that in the below that h of j omega, it the condition itself is given that wm is greater than wc, and given that ws omega s here down. So I'm just thinking that if this condition is satisfied, then we can get the original signal back. But I'm not really sure how this could really work out, because first we need to know that the sampling frequency should be greater enough from the existing signal frequency itself. But then again,
Hmm. That's actually right. Even though you didn't lay it out, properly, but the logic is correct. So see, I'm bound by this. Okay, so I'm saying that the maximum frequency content of the signal is omega m. If my maximum frequency signal is omega m, there is no way my signal can do these very sharp wiggles between two any samples. Okay, so this sampling frequency here is your sorry, is t sampling period, which is 2 pi by omega, right? Omega s. So if a signal can have such a fast fluctuation between a time as small as this, then there is no way that its maximum frequency content is only omega m. A signal that is able to move very fast between you know, two samples ought to have a much faster omega. Okay, and if the signal is really doing something of this sort, these are very sharp edges which actually have frequency at very high frequencies, because signal suddenly changed very fast. So these guys will actually have a frequency representation that is quite wide. Omega m is got to be quite large, and to represent that you need to really sample very fast. Okay, so you need to have an omega s which is much larger, and therefore a t that is much smaller. But once you reach that omega s, once you have determined based on your maximum frequency content in the signal and obtained an omega s, the signal cannot really change too much between any two samples. So the reason the signal is not able to do any funny thing between any two samples is because its maximum frequency content is bound by omega m, which then determines how close these samples ought to be. Okay, so if you think about it, it's quite amazing that once you say that the signal is not able to change very fast because its maximum frequency content is only omega m, you're already restricting how it can change between one sample to another. And actually, you gain nothing by sampling faster. If you say that I'm going to sample very finely, I can do that, but it's actually of no use, because you could have sampled more slowly and still recovered the signal. Once you are beyond the Nyquist rate, you don't need to sample any faster. Okay, does that make sense?
Yes, sir.
Yeah. So it's actually very cool that way. So if I sample a signal fast enough, I have basically obtained everything I need to know about the signal, including what's between any two samples. So now let's move on and get to another question, which is that the signal that I got, X, C, and T, it is still a continuous signal. So I have taken its Fourier transform, and the Fourier transform looks like this. This is the Fourier transform of a continuous signal given by the product of the original signal and a train of delta functions Pt. However, I am going to store it in my computer as 0, 1, 2, 3, a sample, right? When I construct a vector out of this, it's going to be a sample n. So it's going to become a discrete signal. This is xcnt, and I'm going to call it. So this is xpt here, for example. This is a function of time. This is a discrete version of this signal. Here the axis is n. Here the axis was t. When I get to my computer, the vectors look like this. I gave you 4096 samples, right, of the LFP signal. Unless I tell you what the sampling frequency is, you really don't know what the sampling frequency is. All you have got are 4096 samples. I could have sampled it more slowly. So it's the same signal now sampled more slowly here. But in the frequency domain, it's again the same thing. Sorry, not in the frequency domain. In the discrete domain, this is sample 0, this is sample 1, this is sample 2, and that's how I've drawn it. Sample 0, sample 1, sample 2, sample 3, and sample 4, and so on. So now the question is, this discretization, how does that represent the Fourier representation? So remember, I will take the Fourier transform of this signal. I'll take the Fourier transform here. But here now, because this is a discrete signal, I'll take the discrete time Fourier transform, DTFT. And the question is there a relationship between the Fourier transform of the continuous sampled signal and the discrete time Fourier transform of the samples? So what do you guys think? Should there be any relationship? There ought to be some relationship, right? So let's think this through. So I'm going to get to the math in a bit here. But what's the main difference in these two cases? When I talk about the Fourier transform here, and this is signal, this is time domain, and these are samples here, and this is discrete domain, so it's just 1, 2, 3, 4 to n. What's the main difference between the two?
Periodicity.
Huh?
Periodicity.
What do you mean by periodicity? There's no
Um,
periodicity in these signals.
no. So the Fourier transform of a continuous signal is aperiodic, but DTFT of is periodic.
Um, well, so the Fourier transform of the sample signal is also periodic. That's what this
Hmm.
is,
Yes.
right? So the Fourier transform original signal is not. The Fourier transform of the sampled signal is periodic. This is how it looks like. So my question is, what is the main difference between this and that? Is there some information that's available here that gets lost here? What are we losing going
Energy.
from?
So maximum
Yeah.
frequency. No.
No. So, so don't, you don't have to think too much here. I think you guys are overthinking here. Um, I had these impulses as a function of time separated by t. And I took its Fourier transform. And here I have the same samples, but now the axis is n, not t. So what is the information that I have lost here? Forget about the Fourier and the DTFT. Going from here to there, in the signal, what have I lost? Anyone? Actually pointing there.
Still no clue, sir.
Huh?
Still no clue.
Still no clue. So I have lost information about T itself. Here, I can't tell what T is.
Okay, got it.
Right? So it could have been, so here T is equal to some T1, it's twice that of T1 here. When I look at these plots, I know what T is. When I look at these plots, I don't know what T is because it's a 0, 1, 2, 3, 4. So the signals will look the same, the representations look the same, but when I have discretized it completely, I have lost information about the spacing in time between any two signals. I've lost information about t. I have not lost anything else. Okay. Correct? Are you guys with me? So the only thing I ought to lose then, going from, if this is my Fourier transform and this is periodic and all that, is that I will not know what omega s is. Omega s, remember, is 2 pi by the sampling frequency. So the DTFT will actually be just between minus pi and pi. Okay, so I've omega s is in frequency, it's in hertz. To know this, I need to know what the sampling frequency is, which is, sampling frequency, which is omega s. When I discretize it, the DTFT is just going to be between minus pi and pi. So you don't have any information about the sampling frequency anymore. It's periodic with a period of 2 pi, while the continuous version of that signal, the sampled signal, is periodic in the frequency domain with a period of omega s. Okay.
Yeah. Yes, sir.
So that's what I'm going to show you here. That's mathematically it's the same thing. I've got the sampled signal xpt, which is xcnt, delta function of x t minus nt. So it's a delta function sitting at nt with a coefficient equal to xc nt and a sum of all such delta functions. So this is my periodic signal shown. Where is it? Where's the signal? There. So this is what I'm writing as xcnt delta t minus nt. And the Fourier transform, which is obtained by just, it's the standard formula, xpt e to the power minus j omega t dt. You integrate and notice that the xpt has a delta function. That delta function, when you integrate by shifting theorem, it will just take the value of omega, value of t as nt. That's where the delta function is sitting. So the Fourier transform is just going to look like this. Correct? This is when you integrate and then put xpt as this whole thing, and then using the shifting property of the delta function. So this is the Fourier transform of the continuous signal. Now, if I look at the discrete signal and compute its DTFT, so the formula then directly is this. Remember, this is DTFT formula here. This is the DTFT formula. It's a discrete time aperiodic signal. This is the formula. And I note that xdt is just xcnt. So the DTFT here is nothing but the samples of xp at j omega by t. Okay, so I put if omega by t here. So I put omega by t here. This tt gets cancelled. I end up getting this. So essentially, the two representations are identical, except that there's a scaling factor, information about t here, which gets lost in this. So while your xpt will be periodic with a period of 2 pi by t, here it's going to be just between minus pi and pi, or 0 and 2 pi. It's a little bit trickier to understand this mathematically, but the Fourier representation in the time domain, in the frequency domain is quite clear. The ft is going to look like this, and when you want to do the dtft, you just replace this by minus omega and omega. You have lost something here. You knew about omega s here. You don't know about this. This information needs to be provided separately. If I just give you 100 samples of a signal, there's no way for you to find out what the spacing in time between those signals were. This is 0, 1, 2, and so on. So in the DTFT, you lose that. You get a representation between minus pi and pi. Okay, beyond that though, I mean, there's a clear relationship between the original Fourier transform that you were interested in and the DTFT of the samples that you can now actually compute. Okay. So here's what the same thing that I was showing you earlier. I have xc omega, which is the original signal, and this is the Fourier transform of the original signal, and it's band limited. I discretize it. Well, I haven't discretized it here yet. I look at the samples of this, still a function of time. So it's a continuous signal, but it only exists, takes non-zero values at intervals of t. The Fourier transform of that continuous signal will have copies separated by 2 pi by t1. So if you sample slow or fast, these lobes will go move in and out. And if you don't sample fast enough, they will alias also. But if I call these nt as n essentially and make a discrete signal out of it, I've lost something. I've lost information about the time. And then, oops, okay, something is not right. Okay. So sorry about all of this. It's just pen not working properly. Then the discrete time Fourier transform of the samples will look similar to this, except they will be separated by 2 pi. So this is the relationship between the original signal, the sampled version of that, and the discrete version of that for two different sampling rates. Please take a moment to digest this. This is at the take of several classes worth of stuff. So, and this does get confusing, but we just have one more thing to look at, and then we are done. We're actually done with the whole thing. As I've said repeatedly, this is almost worth 2 courses worth of stuff. This is not straightforward, and it takes a while to sink in. So if there are this anything that's confusing you, please go ahead and ask. Chances are your friends are also confused. Okay, so I'm assuming then that we are fine.
So,
Somebody had a question.
So a slight means a naive question. So when we transform it into the discrete domain, discrete function, so the remaining part of the curve gets overlap between this between the period of 2 pi, right?
You're talking about this thing here?
Yeah.
Yeah, there's an it starts after every 2 pi. This was repeating after every 2 pi by t1.
Yeah. Okay.
So yeah, so the DTFT always repeats between 0 and 2 pi. That's always the case,
Hmm.
right?
Hmm.
Does that answer the question that you had, or
So yeah, that answered first. So what I'm thinking is that in the first one where you have a continuous signal where like there is like a complete we sample it and it goes over a time period t. No, here only here the in the slide itself.
yeah, so the continuous, and I've sampled it. So this is my XCT, this function here, which
Yeah.
is 0 everywhere, and then it takes these values. Yeah, this is XCT.
So when we convert it into discrete, so the x-axis is bound by minus 2 pi to plus 2 pi. So the remaining
No, no.
part of
So this is the time domain.
Mhm.
This is time domain. So what? So XC here it's XC at minus 4t, minus 3t, minus 2t. Well, so sorry, minus t, minus 2t, minus 3t, 0 t, 2t. But I'm going to call this 1, 2, 3, 1 when I discretize it. So the
Mhm.
discrete signal has no information about t. It's just 0, 1, 2, 3. It's a discrete signal.
Mhm.
So this is in the time domain, and in the frequency domain, you lose information about omega s and it becomes pi. So that's how they are related. This is the Fourier transform and this is the DTFT. They look very similar, except one has a period of 2 pi by t1, the other one has a period of 2 pi.
Huh. Okay.
Yeah, I can't.
Okay.
Does
Okay. Got
that
it.
answer the question?
I,
Okay.
I'm just like I don't know, is it dumb or not? So in this slide itself, where we have like at t equals to t2 equals to 2t1, where we have
Hmm.
like five spikes, but when we convert it into it becomes only the three peaks
No,
bounded.
no, no, no. So this will keep happening.
Ha
They
ha
are just showing you three,
ha
but minus 4 pi, 4 pi,
ha
6
ha.
pi. They are both. There are infinite copies of everything. They're just not showing them,
Hmm.
but they are both periodic in the frequency domain.
Yeah. Okay. Got it.
Okay. All right. So now we are
Small
at the
doubt.
final. Huh. Yeah, yeah.
So for this, when we have go from the Fourier transform to DTFT, there in this figure it is shown that the spacing is much larger in Fourier transform as compared to DTFT. Is it just
No,
because of
no,
the
there's no
figure?
difference in. Yeah, yeah. It's
Mhm.
just the way it's drawn. That's it.
Yeah, yeah.
The spacing means whether these are coming close or not. It's just a scaling of this whole thing because you are in
Okay.
the frequency axis and the radian axis here. But it's basically something like this. It's just you choose how far you want to make 0 and 1. There's no right answer here, right? So it's the same thing.
Okay.
Okay. So you might be wondering why we have a fifth category here when you had only two categories here and it's two counterparts here. And I'll tell you the reason straight away. In fact, before we get to the math, which is a little bit involved, I want to give you the logic here. So I have got some samples, right? So I've got, let's say, some samples like this of a signal, right? Like the previous one here. And I want to take its as a vector. This is the only thing you can do. You can take its DTFT only. You can't take the Fourier transform and all that. You can infer those things, but at the end of the day, you would be computing DTFT only. But the DTFT is continuous in omega with a period of 2 pi. Right? So it is continuous in omega. So you need an infinite number of values in the frequency domain to represent the signal here in the time domain. This signal has an needs an infinite number of values between 0 and 2 pi to be represented because it's not a periodic signal. Right? So now here's where we can apply a trick. And we can say that, okay, this one is, so if I had this signal and it was 0 everywhere, sorry, I changed the pen color. Then I would have needed all of this. And then it makes no sense because I really need to, the frequency representation is continuous. However, I know one transform here which only needs n terms. And this is the discrete Fourier series. So I say, can I make a periodic signal out of this? And sure enough, you could, if the signal has finite length of n. So I've got 0 to n minus 1. Then all I need to do is take this signal and repeat it after every n. Okay, now you and I have an understanding here is that only the one period between 0 to n minus 1 is of importance. The actual signal is 0 everywhere else. So it doesn't matter what it's doing to the rest of this. It could either be 0 everywhere or it could be repeating. I don't care because anyway, I'm only interested in my signal between 0 and n minus 1 in which the two signals are identical. Okay, so this is the signal xn and this is the continuous version of the periodic version of the signal where I have made an infinite number of copies of that. Now, because this is a periodic signal of length n, I can talk about its discrete Fourier series, which I know will have n terms. Okay, does that make sense? Now the question is, what is the relationship between the DTFT of this signal and the DFS of this periodic signal? And the answer that I'm going to give you is actually the main thing here. Turns out these are just n samples between 0 and 2 pi of the DTFT. Okay, so the discrete Fourier series of this is just you take the samples of the original DTFT at 2 pi by n k, where k goes then from 0 to n minus 1. Okay, so if you have got a finite length signal, you could think of a transform which is a sample, which are n samples of the DTFT. So it also has a length of n. If the signal has length of n, this transform also has a length of n. It happens to be, and I will prove this to you, it happens to be the n samples of the DTFT of a signal which was n here and 0 everywhere else. and it also happens to be the discrete Fourier series coefficients of a signal that is obtained by periodically appending this original signal of length n. Okay, and this is called the discrete Fourier transform. Discrete Fourier transform is nothing but either you can look at it as the discrete Fourier series of a periodic signal obtained by making infinite copies of the finite length signal that was given to you, or it can be thought of as n samples, n equally spaced samples in the frequency domain of the DTFT of the signal that you would have got, which was zero everywhere else except between 0 and -1. Okay, I'm going to prove this to you in the next few slides. But basically, this is the main logic. When I give you a signal, it's got to have some finite length, 4096, right? And I want to look at the frequency representation of that. So I can just compute the discrete Fourier transform, which I'll show you the formula, but it's actually just the samples of the DTFT or the DFS of this, and then I'm done. From these n samples, I can reconstruct this periodic signal, and I don't care about what's between, before 0 and after n minus 1. Between 0 and n minus 1, it's the same as what what the original signal is, and that's all I care about. Okay, so when I bring the signal into the computer, I always compute the DFT. And FFT is just a fast way of computing DFT. So whenever I say look at the FFT, essentially I'm always computing this. There's nothing else to compute.
So is it like that, first of all, we have a finite length signal,
Yeah.
and then we make it periodic, and so DFS has the periodic signal for a series, has the periodic signal in time and frequency. So what we computed in the finite length signal, we compute the same Fourier series, and since Fourier series will be again periodic, we'll consider only one period, and that would be DFT of our signal.
Yes, that's right. Okay, so you don't end up creating infinite copies and doing it that way. The math is equivalent. So I'll just show you what the math is. So here's how I'm going to do this. I'm going to first start out with an aperiodic signal sequence xn, which has a Fourier transform. This is the DTFT. So this is the, oh gee, come on, what is going on? Okay, now it's gone. Sorry, today this pen is acting up very badly. So I've got a signal here, which is of finite length. Let me just draw this here. So I've got a signal of finite length like this, let's say. Okay, and that will have a DTFT, which is between, okay, so 0 and 2 pi. Okay, so it's a periodic signal between 0 and 2 pi. This is xn. But it is continuous. You need values at each omega here. Now I ask that suppose I just take certain samples of this. I take n samples in the frequency domain, not in the time domain, in the frequency domain. So assume that a sequence xk is obtained by sampling x e to the power j omega. This is this dtft at frequencies given by 2 pi k by n, where n varies from 0 to n minus 1. So I have taken n samples of the dtft. So I get this xk, which is x. This is the continuous function. You are sampling it at this. Okay, so now the sequence of samples xk, because they are periodic with a period of n, if I, add 2 pi by n to k, sorry, 2, if k goes beyond n, it's going to become the same as, 0, 1, 2, and so on, right? So 0 to n minus 1. But if k goes beyond that, if it is some to n plus k prime, then it will just be the same as k prime, right? So, sorry, n plus k prime. So this thing is periodic with a period of n. If k goes beyond n, it's the same as, so the 0 and the nth sample is the same, 1 as the n plus 1 sample is the same, and so on. So because this is periodic with a period of n, it could be the sequence of a discrete Fourier series of some sequence x tilde n. So I ask, what is the sequence, a periodic sequence, whose discrete Fourier series is x tilde k? Okay, so I have got xn, I got the dtft, I look at its samples, and I ask, what's the periodic signal x tilde n? This is periodic with period of n, whose discrete Fourier series coefficients are these red dots. Okay, so this is a question that I'm asking, and the answer that I will reach is that this signal is just the original signal with an infinite number of the same signal repeating after every n. Okay, so if I show that, then I'm done. So that's the proof that I'm going to show now. So first I say, okay, I'm going to construct this signal directly from my formula, which is the formula for the discrete Fourier series. This is the synthesis formula for the discrete Fourier series. So it has n terms. Remember DFS, or let me just jog your memory here. So this is, now we are in the discrete Fourier series domain here. So 1 by n, I take n samples and I do this. So that's what I'm doing here. This is the synthesis formula for the discrete Fourier series. Nothing special here. These are the discrete Fourier series coefficients. From those coefficients, I'm asking what the periodic signal looks like. So I put the formula. But now I note that this formula here, xk, are just the samples of the dtft here. Okay, so now I substitute that, noting that the dtft is obtained using this formula. So this is the dtft of xm, which is not periodic. This is the original finite length signal that I had. And when I put this here, I will see that there are two terms which have the same e to the power minus j type representation. Here wnk is just given, is just this. Okay, and I can take those terms out here and actually note that this term becomes 1 every time n minus m is either 0 or a multiple of n. and it's 0 everywhere else. So this thing is actually nothing but impulse train. Okay, we'll do this little bit again, but this is basically it. This is the last thing. Then we are done. Okay, so just pay attention here. This thing here is just the impulse train. So all I'm doing is actually convolving my signal with this, which will then make infinite copies of itself. When I convolve it with a delta function shifted by n, it just puts a copy there. Okay, so we will go through this proof again. We are out of time, but essentially I have, if you believe this for now, you can actually prove that the sampled signal, the periodic signal that I can construct by sampling the DTFT is nothing but the original signal shifted and added. So it's basically just the same signal with copies of itself. The same signal that keeps repeating. That's this. Okay, so I can always think of taking a finite, starting with a finite length signal, making infinite copies of itself. I can always recover the signal back. And this thing has a discrete Fourier series given by this formula. And it will only have n terms. So in the time domain, it's also n. In the frequency domain, it's also n. And that is discrete Fourier transform. This is the formula. Okay, so this is a fair bit to take in. So I will leave you with this. Please go and check this, revise this. This can get very confusing. So you'll have to read this up. But this is it. This is where the math ends. Okay, and this is the thing that we always do when we are given a signal of some length. We always compute the discrete Fourier. This is like the DTFT, but it is not continuous in frequency. You only get k samples, k frequencies spread between 0 to 2 pi or 0 to fs, whatever the sampling frequency is. So these are just the samples of DTFT. And yeah, so we will start again from this part. Please do revise this. Okay, otherwise this can get very confusing. We'll go through this proof one more time, and then we'll start looking at the signal. We are done actually. See, we're back to the signal now. So all the math is coming to an end. We'll just do a revision before the next class, and then we'll be back on with our signal analysis with the real LFP data that we have. Okay, so I'll stop now. If there are any questions, I'll take. Otherwise, we'll meet next Wednesday.